Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to show the relationship between autonomous differential equations and population growth. In particular, first-order autonomous differential equations. So what I want to do is I want to consider this first-order autonomous differential equation. Remember, it's just dy dt is only equal to a function of y, which is equal to 2y. Now, we did some phase graphs of this thing, and I'm going to kind of do them a little quicker here. So if I want to find its equilibrium, remember that its equilibrium happens when the derivative is equal to 0. So equilibrium, this is when dy dt is equal to 0. So we're really just solving 2y is equal to 0, so we're going to get y is equal to 0. So we can see that there's equilibrium right here, y is equal to 0. Now we have to look at the phases as well. As is this thing going to repel? Is this thing going to attract? Is it going to do, repel up here, repel down here, or repel up here, attract down here, and so on. So in order to do that, we have to now graph our y versus f of y, so then I can, investigate, the signs of the slopes of this thing. So really what we're doing is we know that f of y is just equal to 2y, and if I want to graph that, that is going to be a line that looks like this. So remember, this is going to be your y-axis, and this is going to be your f of y-axis, as opposed to this is your t-axis, and this is your y-axis. I'm trying to figure out the relationship between, the location of y and then the thing slopes. Okay, so when y is equal to 0, which is right here, we already know when y is equal to 0, f of y is equal to 0, which means this slope will be equal to 0. We've already drawn it. Now, when y is equal to 1, 2 times 1 is going to give us an output of 2. So when y is equal to 1, these are now going to have slopes of 2. So they're going to have slopes that look like this. If I pick y is equal to 2, we're going to get 4 back. So at 2, we're going to have steeper slopes, so it's going to look like this. Pretend those are slopes of rise of 4, run of 1. But I'm really just trying to show 2. So we can see that when I go in the negative, so if I say negative 1, we're going to get a negative 2 back. And if we go negative 2, we're going to get negative 4 back. So I can see that these things are going to be negative down here. So we're going to have negative slopes down here. So they should be a little steeper as I go farther away. Okay, so if I want to draw some solution points of this thing, let's say if I have an initial value of, these are going to be our t comma y's. If I have initial value of, I don't know, say y is equal to 1, for instance, right there. And then t, it doesn't really matter because we can see that the slopes are the same for all t's. But it's going to still locate us somewhere on this, this horizontal axis. Let's say just 1, 1. So 1, comma 1, we can see this is going to be that point right there. And since it's got to follow these tangent lines, we can see that it does this. Boom. Okay. Now down here, you can see that these would be negative. So if I picked a different solution point, I'm going to get a different, well, this looks like an exponential equation. So that's kind of why we are looking at autonomous first-order autonomous differential equations with respect to population growth, because I can see that the solution to this differential equation looks like an exponential equation, and that's what it is. So let's find this thing's solution because it's separable and really just verify that, this pink curve is really what we're supposed to get here. So if I wanted to solve, dy dt is equal to 2y. Well, I said it's a separable differential equation. I can put all the y's on one side, all the x's on the other. So, I'm sorry, the t's on the other. So this is going to be, I'll leave it 2. So let's go 1 over y dy is equal to 2 dt. And since I now separated these things, I can integrate this on both sides. So this is going to give us the natural log of the absolute value of y, and this is going to give us 2t plus c. Now, solving for this, we're going to exponentiate both sides. So exponentiate is going to get rid of that natural log. So then y is going to be equal to e to the 2t plus c. And since the addition of powers is the same thing as, the multiplication of these factors, this would be e to the 2t times e to the c. And e to the c is just another c, so let's just call it big C e to the 2t. That big C being e to that c. And, it's not really a big surprise that we got an exponential equation as the solution to this differential equation really is, is this thing right here. Now, it's not exactly this. If I wanted to find this actual curve, I need to make sure that it goes through the point 1, comma 1. So when t is equal to 1, y better be equal to 1, and that'll help us find that c. So if I want to go through 1, comma 1, well, that means this is your t, this is your 1. So then 1 is going to be equal to c e to the 2 times, 1. So that means 1, let me just put this in yellow. So that means 1 over e squared would be equal to c. So finally, our solution is y is going to be equal to 1 over e squared times e to the 2t. Simplifying, e to the 2t divided by e squared. Which is going to be equal to e to the 2t minus 2. It doesn't matter. Either way is fine. This is fine too. But again, we can see that, yes, this was an exponential equation, and it really did give us exactly what we expected, this exponential equation. Okay, let's do a slightly more complicated one. And really my goal is to show that what about logistic equations, and are they also solutions to these first order autonomous differential equations. So we will do it this way like I did in the previous video, and then we'll kind of verify it using separable differential equations to show that we do get, logistic curves. All right, I'm choosing this first order autonomous differential equation that clearly has 2 equilibrium points because it's kind of a famous one that we build our logistics equations from, because I can tell that it's going to have 2 equilibrium points because there are 2 spots where this thing is going to be equal to 0 because I have a second degree polynomial here in terms of where the input's going to be your y's. So clearly when y is equal to 0, this entire thing is equal to 0. And also when y is equal to k, because if y is equal to k, this would be y over y, and I'd have 1 minus 1, which would also be equal to 0. So I can immediately tell you that I'm going to have 2 equilibrium points. So we can tell that this is when, y is equal to 0, and also when y is equal to k. So I know if I was going to graph this over here, I'm going to have 2 equilibrium points. We definitely have it when y is equal to 0, and we also have some k up here that's going to also be an equilibrium point. And my goal really is to show you, I'm sorry I'm going to give away the answer right now, but I'm looking for something that looks like this. And if you remember this is a logistic equation that relates to population growth because we have this k, which is considered that carrying capacity. So what happens is with your population, it's going to grow without bound in the beginning, so it's going to look very exponential at first, until you start running out of resources or reach some capacity through size and resources. So it's going to level off to this carrying capacity. And this is that logistic curve. So I really want to show you that, hey, this actually gives you that. And I'm going to solve this differential equation. So if I want to find the tangentials of this thing, we know that I I can just set this up as y is equal to this thing. So I have, f of y is going to be equal to ry times 1 minus y over k. And again, we have our zeros here and here. So I really just want to, investigate when, this thing is positive. Now, it really kind of depends on the signs of k, r and k, and let's just kind of assume r is greater than 0, and then also k is greater than 0. And it'll make our life a little bit easier. So really, if that's kind of the case, I can just investigate this y times 1 minus y. And if I just let them, r and k be equal to 1, because those will at least both be equal to 0. So it'll have the same shape, but it'll stretch it a little bit. So what I know is this is going to be y minus y squared. So this is really a parabola that opens down. It's got solutions 0, 0, and 1. So it's going to look something like, it's going to look something like this. So this being 0, this being equal to 1. Because again, 0 and 1 are equilibrium points. Because that's when the slope is equal to 0. Remember, this is equal to the slope. This thing is equal to the slope in a way. So we know it's negative down here, it's positive in between, and then it's negative down here. So we just kind of proved that down here I'm going to have a bunch of negative tangent lines. And up here I'm going to have a bunch of positives. So these are going to be positive. They'll steepen up in the middle. But then they're going to have to level back off, because remember that these solid blue lines are, asymptote lines. And then down here is just going to be negative. So it's going to look, these are going to be negative. So if I have solutions down here, they're gonna, they're gonna look like this down here. Solutions up here, which is what I was trying to show, is that it's gonna follow these tangentials, so it's gonna have to look something like that. And then solutions up here are gonna look like this. Now I really only tried to investigate this middle area of the curve, because I'm gonna assume that population doesn't start negative, so we're gonna get rid of that. And the population is not gonna start above its carrying capacity, so we're gonna get rid of that. So we're really only just kind of investigating the bounds of y between 0 and k. So let's go ahead and solve this differential equation by separating it. And then we'll talk about all these constants. So if I want to solve this equation, what I'm going to do is anything with a y is going to go on one side, anything with a t is going to go on the other side. So honestly, we're just going to leave the r and then put this this factor and this factor that has the y's in it on the other side. So we're going to have 1 all over 1 minus y over k times y and dy, and this is just going to be equal to r dt. So again, integrating both sides. Now integrating this side, the easy part. This is going to be rt plus c, so that one is the gimme, rt plus c. But over here, if I'm going to integrate this, I'm going to have to break this into partial fractions. So this is going to be equal to the integral of, well, something over this denominator plus something over this denominator. Let me slide this over, I need some more room. Now, we can use Heaviside method if we want to as well. What makes this 0 is when this is going to be equal to k. And then we plug in k, so that means this is going to be 1 over k. And what makes this 0 is going to be 0. So when y is equal to 0, this is going to be equal to 1. So this will be equal to 1. Now, you can do that algebraically as well, but that's just partial fractions. You can check out the video in our Calc 2 section if you want some more work with that. So, partial fractions. Now, when we integrate this side, I got that backwards. That is my bad. This was 1, like I said, and this is a 1 over k. So now when I integrate this thing, this piece right here is going to be the natural log of 1 minus y over k. And this is going to be plus the natural log of the absolute value of y. And then this, like I said, is rt plus c. And you can check that. Take this thing's derivative. It's going to be 1 over this thing times the derivative of what's inside. which is going to be, actually I have to be careful, the derivative of what's inside is going to be negative 1 over k. So I don't need a negative, I need a positive, so this is going to actually have to be a minus. Now I'm going to switch this thing's order because I want to condense these natural logs, and in order to do that, I'm going to use the property of natural log that says the subtraction of two logs is going to be the single log of the division of these arguments. So what I mean by that is the natural log of y minus the natural log of this binomial is going to be the natural log of y divided by that binomial. And over here we're going to have still our RT plus C. All right. My goal is to really solve this for y. That is why I'm trying to condense these things. I'm looking for a y equals, and I'm really trying to verify that I get this pink logistic curve, okay? So in order to solve this, now I'm going to exponentiate both sides by e. So y over 1 minus y over k is going to be equal to e to this thing. And very similarly, we just did this, so this is going to be e to the rt plus c, but I can do e to the c, so I can just call this c e to the rt. Now, how am I going to make this work? Well, what I need to do is I'm going to have to try to isolate the y's here. The problem is on the bottom I have this 1 minus y over k. And what I want to do is my goal is to say y equals. That's kind of my job. So in order to do that, I need to expand these things. So the problem is I got y in the denominator and also y in the numerator. So I'm going to, sending this up here, I'm going to multiply both sides by this denominator. So this is going to be equal to c times 1 minus y over k e to the rt. Now, these things being all multiplied together, a bunch of factors isn't going to help. What I need to do is I'm trying to get y on one side. So if I can expand these things, I can isolate through addition and subtraction. I don't want to do it through division because it's going to send the y back in the denominator. So y is equal to, this is going to be c e to the rt, here. And then finally, this is going to be equal to c times this, so c times y over k times e to the rt. So this is going to be c y over k e to the rt. Now what I can do is, since I have our y's in, as additions and subtractions, I can send this term over to the other side. So y plus cy over k e to the rt is going to be equal to c r t, and I can finally isolate my y by factoring out. So this would be 1 plus c over k e to the rt is equal to c rt, and then divided by this denominator, I'm going to have by this factor is going to be equal to c e to the rt all over 1 plus c over k e to the rt. Which honestly was my goal, is to show that this is a logistic curve and that is a logistic curve. So we can see how this does relate to population growth as far as just being, growth without bound. And then we can see also logistics. We can see that this growth with a carrying capacity as well. So if you like the videos, please consider liking, subscribing, and sharing. Thank you.